All right, lastly, in our section 2.6 notes, we're going to discuss limits of rational function. And so here's just some reminders of notation that we've already talked about. These one-sided limits here that we discussed whenever we talked about piecewise functions. Okay, notice the minus sign that is the superscript to the a there. That represents approaching a from the left side. And the superscript plus sign right there represents approaching a from the right side. And then these bottom two limits are your end behavior limits. Notice that they are x approaches negative infinity and positive infinity, and the end behavior always deals with the horizontal asymptote if there is one. And so we're going to make sure that we make the connection there that limit as x goes to either positive or negative infinity of a function f of x is really just asking for the horizontal asymptote whenever we look at the graph. Okay, so here's a nice example of a rational function. I've got you 6 questions to answer here as far as limits are concerned. And so let's see if we can attack these one by one. So in letter A, we've got the limit as x approaches -3 with a plus sign as a superscript. So remember, that means from the right side of -3. So if I look at this function from the right side of -3, this is -3 right here. And so if I approach from the right side, I just need to jump onto the function somewhere and see what the y values are doing as I approach -3 from the right. And so as x, here's the x-axis, as I approach -3 from the right on the x-axis, what's happening to the y values? Well, hopefully you said they're increasing without bound. And so that tells me that this limit is going to equal to infinity. Okay, what about if I approach -3 from the left? That's what letter B says. Well, if I jump onto the function somewhere to the left of -3 and then approach -3 on the x-axis, what's happening to the y values? And hopefully you again said that they are getting bigger and increasing without bound, and so therefore that limit is also going to be positive infinity. Okay, letter C, x approaching 2 from the right. So here's x equals 2. If we jump on the function somewhere to the right of 2, that would be this piece over here. So notice these pieces don't matter for this particular question. It's just this piece of the rational function, this rightmost piece, that I'm going to look at. So let's jump on somewhere, let's just say here, and approach 2 on the x-axis from the right. And what's happening to the y values? Well, hopefully you said that they are getting really negative and decreasing without bound. And so therefore this limit is going to be negative infinity. Now for letter D, x approaching 2 from the left side, just jump onto the function somewhere to the left of 2 and then see what the y values will do as you approach 2 from the left. And so hopefully you're saying that they are increasing without bound, which means that my limit there is going to be positive infinity. And then E and F are my end behavior limits. And so for E, the limit as x approaches negative infinity, that's going to be the left end of the graph. And so here's the left end of the graph. And as we let x approach negative infinity, what's the y value that the graph is approaching? And if you can see this line right here, I dashed in your horizontal asymptote at -3. And so this limit is going to equal to -3 to represent that the horizontal asymptote of this function is y equals -3. Now the other direction, x approaches positive infinity, that's the right end of the function. And so we're going to concern ourselves with this piece of the graph now. And notice that as x increases without bound, the y values again approach -3. And so this limit is also going to be -3. Now for a rational function, those two end behavior limits will always be equal to one another as long as they are finite or numerical, meaning as long as they're not infinity or negative infinity, they are always going to be the same as long as the function is a rational function. That's not always the case. So for example, for a logistic function, those two in behavior limits are actually most of the time different. But for rational functions, which is what we're talking about here in section 2.6, these two limits are always going to be the same as long as they are numerical or not infinite. And so that's going to do it for section 2.6. This is all building up to a method called the Rady method. And so the Rady method is just an acronym, R-A-T-E-Y, and this is the method that we're going to use to graph rational functions. And so that's what your next set of notes is on. And until then, hope you guys have a good day.